Hello, I'm Ryan.
And I'm Catherine.
We're part of the BlendJet team.
And husband and wife. If you're one of the 5 million people who use a BlendJet portable blender, thank you.
A few years ago, I had a freak accident and almost died. Daily smoothies have helped me recover.
We created BlendJet to help people live healthier lives by making it easy to enjoy perfectly blended smoothies and protein shakes anytime, anywhere.
The BlendJet 2 portable blender is powerful, USB rechargeable, cleans itself, and comes in over 30 colors.
Get yours now on blendjet.com.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again. Thank you, as always, for joining us on the Space Nuts podcast. It's all about astronomy. Episode 203, I might add. My name's Andrew Dunkley, and with me, as always, is Professor Fred Watson, Astronomer-at-Large. Hello, Fred.
Hello, Andrew. Of course, we do more than just astronomy. We do space science and a bit of physics, and occasionally talk about relationships and things like that.
And birds.
Birds, yeah.
As it turns out.
Well, we'll do anything.
And cats. Cats get a mention.
Yeah, actually, the cat is on, he's fast asleep on the lounge at the moment, so we're probably not going to hear much from him.
How very unusual for a cat.
Yes, it's strange, isn't it? It's not often you see that.
It is, rather. I'm a little bit excited today, Fred, because we actually get to use our first ever audio question.
Isn't that great?
Because we now have people we now have a service where you can log onto our website and record your question with your own voice, and we can drop it into the program. And we're going to do our very first one of those today, which is, a little bit of a different way of doing it. But I think it's great that we'll be able to hear the voices of the people who listen to the podcast. So that'll be fantastic. We'll get into that later. There's also a question about star formation that has got one of our YouTubers a little bit confused. So we'll see if we can solve that problem. And we're going to talk about harmonic stars. There's one particular cluster of stars that's doing something a little unusual. I'm not sure if that means it's singing or releasing a pop album or something to that effect, but we'll find out. But the first thing we want to talk about today is X37B, this space plane, Fred. This was launched on Sunday from Cape Canaveral on its, I think, 7th mission. And this is the all-mysterious, unmanned, remote-controlled solar flying vehicle that I think in its last mission was in space for over 700 days.
That's right. It's always intriguing when this remarkable vehicle is launched because we don't know why it's going. The last,
which makes it hard to do a whole segment on. Because...
Well, that's right. No, look, we can make up all kinds of things. The last time it was launched, I think you and I might have talked about it on the podcast because we always tend to home in on this extraordinary space shuttle. You know, it's a quarter of the size of the traditional NASA space shuttle. It, in fact, was originally designed by NASA, but was very quickly taken over, I think, by DARPA, the Defense Research Agency in the United States, and promptly became top secret. It's called the X37B, and basically is a quarter-sized replica of the space shuttle, a few design changes. It launches on top of a standard rocket, and if I remember rightly, this one is on top of an Atlas rocket from the United Launch Alliance. Yes, it's an Atlas V rocket, and it's also got another national security satellite in the payload bay. But as you said, launched successfully on Sunday, declared a success an hour and a half after liftoff. It would be well into orbit by then because it only takes, less than 10 minutes usually to get to orbit in some of these things. That's an initial orbit, but it's probably in its final orbit now. So the last time it went up, when the media asked the defense agencies what its mission was, the answer was testing.
Yes.
And that's
an open-ended answer. Yeah, testing.
Testing, yeah.
That could mean anything.
the missions are all about, they're all about checking out technologies and things of that sort. And one reason why it excites me that this sort of thing is taking place is because you can look back on technologies that have been developed for military space missions, which are now common parlance in civilian space flight. So whatever is learned from the X37B mission might very well stand us in good stead one day, and the sooner the better, in terms of how you maneuver in space. In fact, I think the original mission for the X37B, if I remember rightly, and it's several years ago now, was to look at the dynamics of orbit changes, how you can be nimble in orbit, because changing the orbit of a spacecraft is not a small matter. You've got to put a fair bit of oomph into it to shift it, particularly if you change the orbital inclination. So I think that sort of thing is the sorts of experiments that have been doing. The home base of the X37B, and there are two of them which are operated by the Air Force. Their home base is it was the Space Shuttle hangar at the Kennedy Space Center. So they've gone for miniaturization. And just to put a few statistics into the story. First flight was in 2010, further back than I thought it was. It's these things creep up on you. And totally, so far, they've totaled 2,865 days in orbit. And of course, there's another 3 days or something since then, because that was as of last Sunday. One of the spokespeople, Jim Chilton, who is the senior vice president for X37B at Boeing, he said a number of things that are quite nice comments on this, as much as you can say. The X37B stands on the shoulders of the Space Shuttle, and from a common shape to a common home. That's his reference to the fact that it lives in the Space Shuttle hangar at Kennedy. But what he also says is, if you add up all the missions, just under 8 years in orbit and 1 billion miles. So a lot of traveling by this machine. Quite interesting stuff.
Incredible.
And I think... Sorry, just one final comment, Andrew. Sorry to interrupt. You might have been about to say this, so I'll shut up and let you say it.
No, go ahead, because I was just I was going to say, and this aircraft was or spacecraft was built by Boeing, which might surprise a few people. It's a Boeing plane, and when you go to the Boeing website, it's got on the front page it says purpose. The purpose of the X37B. It's 3 lines. It's a 3-line explanation of the purpose of the X37B.
Yes.
So they're not letting a lot of information get out too far. And when you're talking about a vehicle that's operated by the U.S. Defense Department and Air Force through the Pentagon, it does sort of set off a little alarm bell in the back of your head. What else is going on up there is the first question that pops into many minds, I'm sure.
That's right. This is just the tip of the iceberg. This is just this exhibit having a replica, which we should mention is completely remotely controlled. There are no passengers on board, but a replica of the Space Shuttle doing extraordinary things, things in orbit, and then doing its landing in exactly the same way that the Space Shuttle did, gliding down to a touchdown. Remarkable stuff. The only other thing I was going to add to the comments, Andrew, is that I think this launch of the X-37B was under the auspices of the new Space Force in America. Even though I think it's operated principally by the Air Force, but I think I'm right in saying that this is the second rocket launch for the newly established Space Force. The first one was back in March. So the Space Force has got its got its fingers in this pie as well. I wish we had. It'd be lovely to know what it's up to.
Yeah, and once again, anything involving space comes up with a fantastic name. That sounds like something from a B-grade science fiction film, The Space Force.
Space Force. I know it does.
Yeah. I did see one little article about this particular mission, and it said something about experiments in space involving seeds. But that's all I know. It doesn't really say much more than that.
Right. Okay.
But as you say, it's about the size of a pickup truck. What might surprise a lot of people is that this concept first came into play in 1999. So this has been a long-term venture, and it took them another 11 years to get one into orbit.
Yeah.
So it is quite remarkable. But if there's some sort of benefit to future space travel or humanity in general, it's certainly something that needs to be endorsed. But you do continually tend to sort of have a seed of doubt in the back of your mind, and that's not what the experiment's about, because of all the secrecy.
Seeds of doubt. Ooh, I like that.
But there's so much secrecy, and I suppose when you're talking the Pentagon, fair enough. But you do have to wonder what else is going on. Are they working on new space-based weapons or something like that? And it's all subject to specation.
That's right. Although there was an assurance, it was a number of years ago now. Excuse me, Andrew. By the Pentagon, this was in advance of one of the earlier launches of the X37B, that they weren't testing weapons. That was an assurance that was given. So that may or may not be true now, but certainly for that particular mission, nothing on board that could shoot stuff down, and probably not now either.
No, but we watch with interest. Look, it's not that they're not hiding it. I mean, how do you hide a rocket launch at Cape Canaveral? It's pretty darn obvious when it happens. But there's plenty of footage of this thing, and it's a pretty sleek machine. And they talk about it. They just keep some of the actual hands-on stuff that they're doing completely away from prying eyes and ears. So, and that always leads to conspiracy theories and the like. So, secrecy always seems to lead to some kind of conspiracy theory, doesn't it?
Yes, it does. And conspiracy busting is part of our job here on Space Nuts, Andrew. So, I mean, there are probably plenty of conspiracies around X37B. If we knew any more than we know already, Andrew, they'd have to kill us anyway. So it's probably just...
Oh, yeah. Well, I wish you hadn't said that out loud. But anyway, there it is. We don't know how long this mission's going to be either. So
we know nothing. We know nothing at all.
No, it could be up there for a couple of years, which is what happened last time. So... We will review the data once it comes back. Will we not, Fred?
It will be tests.
Yes, it's up there for testing. There it is. You're listening. Can't tell you anymore. No. You're listening to Space Nuts with Andrew Dunkley and Fred Watson. Now let's take a little break and find out more about our sponsor, ExpressVPN, rated number 1 by TechRadar. This is the one I use. I've been using it for a couple of years and I love it. When I joined ExpressVPN, they were brand new to the market, but I read a lot of reviews and did a lot of comparisons. And there was just something about their business model that I particularly liked. And a couple of years down the track, honestly, can't complain. Their interface is very easy to use. Their service is second to none. I've had to contact them a couple of times about certain things that I wanted to do, and they were brilliant. So you may be wondering why I do need a VPN at all. It's all about privacy. Do you really want big tech companies, governments, and others knowing what's going on with your online activity? Even if you're having nothing to hide, it just feels downright creepy. I think you'll agree. And governments are getting more and more interested in what you're doing every day. And so, protecting your privacy is what VPN is all about. And how often do you run across websites that you want to get information from only to find that they're geo-blocked? This is becoming an increasing problem, but ExpressVPN solves that problem for you. Now, if you go to our special URL, you'll see quite a list of things this service can help you with, things you may never have thought of before. As I say, it's the one I use, secure, fast, and it just works. So protect yourself online today and find out more about how to get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Try expressvpn.com/space to learn more, and you'll find the link details in the show notes and on our website. Now, back to the show.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Once again, I'd like to send out a big thank you to all our patrons who basically support the podcast through patreon.com/spacenuts to the tune of, a handful of dollars a week. Or a month, I should say, and we do appreciate your support. Now, some people have come to us and said, look, I'd rather do it through Supercast. And so we have now got a Supercast page, which is spacenuts.supercast.tech. If you would like to support the podcast through that platform, there is a 30-day free trial, which you can cancel any time. And you'll, as our other patrons do, get access to the back catalogue, weekly new episodes ahead of the general release, bonus material, and it's a 100% commercial-free offering. So if you would like to be a supercaster, you can do that through spacenuts.supercast.tech, and it's $5 a month if you would like to do it that way. Now, Fred, moving on to our next topic, and this one I must confess I've read through, and it's one of these stories that sort of has me a little bit mystified. We're talking about harmonic stars, particularly one star cluster that has been described as wayward in one of the articles that I've read. So what is a harmonic star, and what's so special about this particular cluster?
Okay, so this is about stars essentially pulsating in a way that is almost akin to earthquakes on the Earth. And it's actually, the topic that we're talking about is a branch of astronomy called astroseismology, and that sort of essentially gives you the flavour of it. And one of the things that always delights me about talking about astroseismology is that one of its principal proponents, a gentleman by the name of Professor Tim Bedding, who's at the University of Sydney. Tim and I used to work together. In fact, he was a research assistant for me back in the 1980s, probably. We built an instrument for positioning optical fibers, which had the strange name of AutoFred. AutoFred was essentially something to help you position optical fibers in a telescope. We might talk about that another day, Andrew. But it's always great to see Tim in the media, because he has, not single-handedly, but certainly been very much a leading exponent of this. He's taken forward the topic of astroseismology in a big way. And this is one of their success stories. So, pulsating stars, many different classes of stars pulsate. Many centuries ago, I actually worked on some of them, which contributed to my PhD, a class called Lyrae stars, which are variable stars, and they pulsate by enormous amounts, sort of 50% of their diameter they increase by and then shrink by over a period of about a day. So that's an extreme form of pulsation. But it turns out that all stars have small, low-level pulsations, including the sun. The sun's actually doing this vibration at a level that we can detect because we've got enough light from the sun to do radial velocity measurements of its surface. That's to say, we can use a spectrograph to break the sunlight up and read the barcode of information in it and measure the way the surface is coming towards and away from us, and looking at the pulsations. If I remember rightly, the sun has a basic pulsation period of, I think it's something like 8 minutes, that sort of order. It's just wobbling up and down slightly. But when you look at the science of astroseismology, and this is where Tim and his group at the University of Sydney have done great work, you find that it's not just something expanding and contracting. There are all these different kinds of modes of oscillation which take place within stars. And Tim's group have produced over the years some really neat little video simulations showing the way these stars vibrate. And it's almost like some of them wiggle their hips, some of them are swelling one way and then shrinking the other as they pulsate. These are, of course, highly exaggerated, but they give you an idea of what we call modes of pulsation taking place in stars. And
so there's no constant pattern to this. It can be different from star to star.
That's right. There is a constant pattern, but what you've got is different modes of oscillation all superimposed on top of one another. Think about, all right, the basic mode of pulsation, which is a star just swelling and shrinking spherically. I'm doing hand motions here, Andrew.
Yes, I can see that.
Zencaster, you've got to imagine them. But then you can, all right, so it's just swelling and shrinking. But then there will be another mode where along one axis it's swelling, but simultaneously it's shrinking along the other. So it becomes football shaped for a while, for a short time, and then shrinks back and becomes football shaped in another direction. What you can do,
all right, well, we better clarify that, because in Europe they'll be thinking, well, that's just round. We're talking about a rugby ball or a NFL ball.
A rugby ball, yes, that's right. So it becomes a non-spherical football shape. How's that?
Yeah, there you go.
And then there are many other different kinds of oscillations that can take place. There's one I remember seeing in the simulations where it suddenly, the star becomes pear-shaped at the bottom, and then so the oscillation changes it so that it's like an upside-down pear. These are all different modes of oscillation, and they can all be happening at once. That's the really interesting bit. You might get a basic mode of swelling and shrinking, but then superimposed on top of that, there's all these other different modes of oscillation. And that's where it all gets interesting. Now, cut to the chase in the story that we're talking about, it takes us back to NASA's TESS Space Telescope, the Transiting Exoplanet Survey Satellite, which was built and launched and is operating principally to look for the dips in brightness of stars as their planets pass in front of them. And it's been great at doing that. So we've got fantastic results. But because TESS is what you might call a photometric telescope, that's to say it looks at the brightnesses of stars, it's really good at seeing the way stars themselves fluctuate in brightness. And as they pulsate, that's what they do. Very, very slightly. A star, as it pulsates in these astroseismology modes, will change slightly in brightness. And so what you can do is plot what we call a light curve. This is the way a star's brightness changes over time. And then you find that it's wiggling up and down. But what's complicated about it is that the wiggles potentially can tell you about these different modes of vibration in the star if you can disentangle them. And so, you imagine a trace of the light brightness over a long period of time, and you've got all kinds of random wiggles in it. And what you're looking for is periodicity in those wiggles. In other words, you're trying to sort out, okay, there's probably a basic swelling and shrinking that might be relatively easy to find, but then there will be other modes of oscillation in it, which will be much harder to detect from that light curve. The technique that's used for this is something which is called a Fourier transform. And it's all about a process called Fourier analysis. It goes back more than 100 years, the technique, although it was only in the 60s and 70s that computer programs were able to do what are called fast Fourier transforms, where you're looking for the different frequencies in a note. And the reason why you're talking about harmonics, which is how you introduced this, Andrew, is that this is exactly what happens in a musical note. So if you play a note on a piano, you can tell, even though it's the same note, you can tell the difference between that and the same note played on a trumpet. And the reason for that is because of the harmonics present in the note. And if you wanted to analyze those in a scientific way, you would put them through a fast Fourier transform so that you actually can see what different frequencies are there. Now, so that's basically what's being done in this work on looking at star vibrations using data from TESS. And in particular, Tim and his group, just to once again cut even more to the chase, have looked at a particular class of variable stars, which are known as Delta Scuti stars. They come from the sort of, the archetypal example of this, a bit like the RR Lyrae stars I mentioned a while ago, are named after a star called RR Lyrae. Delta Scuti stars get their name from a particular star in the constellation of Scutum called Delta Scuti, Delta being the fourth brightest of those stars, which is why it's the fourth letter of the Greek alphabet. So Delta Scuti stars have always baffled investigators as to why the way their pulsations work. And what Tim and his team have done is looked at many samples of Delta Scuti stars. I think they've looked at 60, I think I'm right in saying, of this particular class of stars. Maybe not, maybe that includes other classes, but they've essentially decomposed or analyzed the pulsations of these stars to make sense of them. What Tim Bedding says is the definitive identification of pulsation modes opens up a new way by which we can determine the masses, ages, and internal structures of these stars. And that is the great strength of astroseismology. There are things that you can determine from that which give you an independent determination of, as he says, masses, ages, internal structure. So one of Tim's students, Daniel Hay, at the University of Sydney, a PhD student, wrote the software to do this, and they processed 92,000 light curves of brightnesses of stars, and essentially got the results that they want. They've actually worked out what the pulsation modes of Delta Scuti stars is. That's a very big step forward because nobody's understood that before, and it's great that this work is being done. Not very far from where I'm sitting here in Australia.
Wow. I also understand that this could also be a way of finding planets.
Yes. That's right. You will find them by the transit method if the planet is passing in front of your parent star. But if it's not, and it's gravitationally disturbing the star, then there's a good chance that you could do that as well. Just going back, though, to something you said at the beginning of this story, Andrew, you're right about these appearing in clusters, because Delta Scuti stars are basically young stars. And when you look at young stars, you often find that they are still clustered together, like the Pleiades, that little star cluster that we can see from all over the world pretty well, not very far from the Taurus, the Bull. In fact, it's in the constellation of Taurus. The Pleiades are a young cluster. They're 10 million or so years old. They are still together. Eventually, these clusters disperse and the stars go their separate ways over time. But the thing about the Delta Scuti stars is that they tend to still be in clusters. And so these, the what you call associations of young stars can be analysed by this technique. Actually, Tim Bedding's got away with words as well. He says, our results show that this class of stars, that's the Delta Scuti stars, is very young, and some tend to hang around in loose associations. They haven't got the idea of social distancing rules yet. So Tim's putting it in a nutshell. They haven't yet dispersed into individual stars.
Yeah, and there was a little bit of astronomy humour in there as well. But it was funny as a car crash.
I haven't found that yet, no.
Oh, the social distancing I was referring to. But anyway, there it is. No, fascinating, and good that one of your former colleagues has sort of done a remarkable piece of work. It's a testament to all of you. And there will clearly be more to learn from this, and more to gain in terms of other things that we look at in the wider universe, I imagine, Fred.
Yeah, I'd encourage anybody who's interested in following this up to check out the astroseismology web pages, particularly University of Sydney stuff, because you'll see these different pulsation modes that I was trying desperately to describe there actually played out in animations. It's worth following up.
Yeah. And I think the ABC did a good story on it as well on their science page. So you can look it up through the Australian Broadcasting Corporation science website also. You're listening to the Space Nuts podcast, episode 203, with Andrew Dunkley and Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Now, before we get into our questions, just want to say hi to all our social media followers, whether they're on YouTube or the Space Nuts Facebook page, or are part of the Facebook podcast group, the Space Nuts podcast group on Facebook. I always mess that up, but it's a bit of a long-winded way of saying that they're Space Nuts listeners that have created their own environment on Facebook to get together and talk and share ideas, ask each other questions, and it's a lot of fun. Got a great many people there now, so if you would like to be a part of the podcast group, Space Nuts podcast group on Facebook, just do a search for that or some variation of it, and ask to join. And you can also chat with like-minded people from the Space Nuts podcast group, because they're terrific people. And we thank everybody for supporting us through whatever social media platform they choose. Now, one more thing before we hit our first question, Fred. You've been a busy boy. What happened last week?
I had an article published in The Conversation, the online sort of news and commentary organisation, which always has as its subtext academic rigor and journalistic flair. I'm not sure which of those they got from me, but they now have an article on their Australian Conversation website, which is called Technology, International Bonds and Inspiration: Why Astronomy Matters in Times of Crisis. And it's really just, asking the question, well, in an international emergency like the present one, is the science of the stars relevant? Of course, you and I are firmly convinced of that, and a lot of people who listen to us are. But in particular, I wanted to draw attention to the fact that Australia is currently deeply involved in playing a leading role in building what will be the world's largest radio telescope, the Square Kilometre Array. And I wanted to show how that effort can benefit a nation that is actually focused on containing a global pandemic, and why we should be doing that. And it turns out, of course, when you look back through history, that astronomy has been a very resilient science. It's survived many wars, world wars, and indeed Spanish flus and things of that sort, and will survive. But it not only survives, it brings benefits to people, which is why astronomy has always kept up really remarkable public support. And the article shows why, and the answer is in the title: Technology, International Bonds and Inspiration.
Very good. Well done, Fred. And actually, I love that website, the Conversation website. It's very much worth visiting. They cover so many topics in depth and talk to some pretty interesting people. So it's called theconversation.com, and the Australian edition is easy to find as well. So take a peek. Now, something else that's exciting, Fred, is the fact that we've got our first audio question. If people want to ask us questions using their own voice, they can go to the Space Nuts website and just, as long as you've got a microphone readily available through your computer, you can just hit start recording and tell us your name, where you're from, and ask the question. And it's as simple as that. Bytes.com/spacenuts is our website, by the way, BITESZ.com. Bytes.com is our parent company. Bytes.com/spacenuts, and record your question there, as Fraser from Scotland has done.
Hey guys, I'm Fraser. I'm from Peterhead, a small village in Scotland. I'm a massive fan of the show. I've listened to every single episode that you've ever done, and I look forward to listening to all the other episodes you do in the future. I just have a question that I would like you to discuss and explain further on one of the episodes. Basically, it's why does the sun have such little mass of iron compared to its overall composition? It seems to be next to nothing, like less than 1%, whereas the Earth has 30% or 31% iron by mass, which seems to be, it doesn't quite add up in my head. Could you please explain that further, how that came about? Is there a theory? Do we know why that is? I look forward to hearing from you guys soon. Keep up the good work. Cheers.
It's nice to hear a different voice on on the Space Nuts podcast. Would you agree, Fred?
Yeah, look, it was brilliant hearing Fraser. It takes me right back to when I used to live in Scotland. I don't think I've visited Peterhead, but he says it's a small village, but I always thought it was quite a big town. So that's all right. It's good to hear, Fraser. Thank you very much.
It's all relative. Where I live would probably be considered a small village in the United States, but here it's a provincial city
Yes, that's
of 42,000 people, but not overly big in the scheme of things. But let's get down to Fraser's question, and I'll just paraphrase the short version of it. Why does the sun have a low mass of iron? I would say because the sun is actually a male and we all hate ironing, but I could be wrong about that.
That's right. I actually quite enjoy ironing. It's my one duty that I'm good at. So it all comes about because what the sun is mostly made of is hydrogen. And hydrogen's the raw material of the universe, essentially. The hydrogen was formed in the Big Bang. Stars form from clouds of hydrogen, which are slightly contaminated by other things, including iron. So when stars form, inevitably, they are mostly made of hydrogen, and the other elements are there from previous generations of stars, which have produced the iron in their atmospheres. So that's what a star forms from. But the planetary system of a star is just the kind of leftover debris, and it's if you like, it's largely consists of the things that in the star itself are just contaminants. They're just, low-level contaminants. But that, particularly the dust which forms around stars, that's a different, it's different matter. It's silicates mostly, but it's also has quite a high iron content, and that's explaining why the Earth itself has a high proportion of iron in its makeup. It's because the disk of material, the protoplanetary disk that formed at the same time as the sun did, is really just the debris that you might almost call it the solid debris that doesn't form part and parcel of the star itself. So the hydrogen's collapsed into the star. There would still be some hydrogen left that hasn't collapsed. That's why we get gas giants forming. But the small rocky planets are just the really tiny amounts of debris that are formed, that are left over from the formation of the star. I'm probably not explaining that very well, but the bottom line is that stars and planets essentially have different makeups. It's a great question. It's the first time, actually, in 150 years of people asking me questions about astronomy. I think that's the first time anybody's ever asked me that. So well done, Fraser. It's good to hear from you.
Nice work. Well done, Fraser. And thank you for recording a question on our website, and we hope we get many more. There are a couple, I think, that we haven't got to yet. Some of the questions we get, we've answered in previous episodes. So if we don't use your question, that's most likely the reason. Or we occasionally get people asking us the same question, sometimes on the same day, and so we'll answer those collectively from time to time. So it doesn't mean we're ignoring you, and we certainly do appreciate you getting in touch with us with your questions, but sometimes we've already answered them. Although sometimes we do sort of review them, which is what we're going to do now. And you mentioned star formation, Fred. We have a question from one of our YouTube followers who recently subscribed, and his name is Goodfella Jolly. I love the handles of people on some of these platforms. Great podcast. I've been a podcast listener for several years and enjoy your humour and content. I just subscribed. I have a question about star formation I hope you can answer. It seems counterintuitive when you say that gas clouds collapsing on themselves due to gravity. Would not the vacuum of space work against any condensation of matter before gravity could coalesce any substantial amount? Basically, it seems any matter would boil away before it had enough gravity to support any liquid or solid form. It does, conjure up some sort of ideas that clouds in space collapsing on themselves due to their own gravity would be a counter move. So I suppose, because we did talk about this recently, and it's obviously conjured up some thoughts in people's minds.
And it is entirely understandable, actually, when you think about it. So if you think about a liquid on the surface of Mars, that turns into a gas essentially under the vacuum of Mars's atmosphere. Mars does have an atmosphere, but its pressure is only 1% of that of the Earth. So it turns into a gas. But that gas is still clung onto by the gravity of Mars. And that's the bottom line here. The gravitational force is, in a sense, it is the most important force in the whole evolution of the universe, because it works over big distances. And it is not to be denied. It is very insistent. And so if you have, think of the universe after the Big Bang, you've got a universe that's largely composed of hydrogen and helium, the two products of the Big Bang, plus something called dark matter, which is in some ways the elephant in the room here. And it is the elephant in the room because we don't know what it is. But dark matter does not interact in the same way as normal matter, except that it's got a gravitational pull. And we think that it was actually the dark matter that formed the seeds of where galaxies grew. So the dark matter itself clumped together after the Big Bang. We see evidence of that throughout the history of the universe, and that drew the hydrogen towards it. And it's all about gravity. Gravity overcomes everything pretty well, including the tendency of things to evaporate into the vacuum of space. The bottom line is that it's not an evaporation process we're talking about. We're starting off with clouds of gas, and they indeed collapse under their own gravity. The pull of of each individual atom of hydrogen on the next one is sufficiently strong that it overwhelms any tendency to disperse. And so you get this condensation, this collapse. As the collapse takes place, the pressure gradually increases. As the pressure increases, the temperature increases, and that's how stars switch on. And we see, this is such a well-established mechanism for star formation that it is very much part and parcel of the accepted wisdom of the way things happen in the universe. We see evidence from many, many different telescopes of this process actually happening. You can sort of see it taking place. You've only to think of the of those fantastic pillars of creation, the images that came from the Hubble telescope. You're actually seeing exactly this in process there. And those gas clouds are quite dusty, which is why we've got those opaque fingers that actually you can see through in the infrared, but you can see that star formation is taking place under this gravitational collapse. I don't know whether that answers Goodfellow Jolly's question or not, but it is the way it works. And I guess what I would point to is the mathematics of this. The theory is well established. It works. It is the way stars are formed.
Wouldn't you love, Fred, as an astronomer, to be able to get so close as to see that moment when the star is born inside the cloud? I know you say we can see star formation, but we surely cannot see that exact moment of initiation or ignition or whatever it is that births a star.
The thing is that process of initiation or ignition is a good way to put it, because that's what happens is the nuclear processes switch on. It probably takes a million years.
So I thought it would be something that happened like snap of a finger.
What is going to happen is that you will get this cloud of gas, which will have a temperature differentiation in it. And at the center, at the core of it, there will be high enough temperatures that you start to get nuclear processes. But I think the process to get from there to something that looks like the sun is probably quite long. I need to check this because I'm sort of thinking about things that I learned many, many decades ago. Tens of thousands, hundreds of thousands, perhaps even millions of years, I think, would be the switch on time. Maybe not quite as much as that. Look, but it's not an instant. It's something that would happen gradually over time as more and more of the center of the cloud switches on.
And I suppose depending on the density and size of the clouds would result in how many stars it's going to create.
That's right.
Over time.
And to some extent, the mass of the stars that it creates. We know that in the early universe, really high mass stars, 20, 30 times the mass of the sun, were commonplace, and they don't last long. These supermassive stars burn up their fuel very quickly. It's counterintuitive. You'd think they'd last a long time, but they don't. They're very energetic. They emit copious quantities of energy. They have voracious appetites for the hydrogen fuel. And eventually, before too long, a matter of just a few million years, they'll turn into a supernova. And that's the process that lets you spread the heavier elements throughout the universe, which is how we get planets.
It's like garden fertilization.
Exactly that. That's exactly what it is. You got to dig.
All right. Thank you for the question, Jolly. We really appreciate it. It was thought provoking and gave us plenty to talk about. Thank you to everybody who's sent us questions lately. We're going to get to as many as we can. We've reached a point where we cannot answer all of them, but we certainly do encourage you to record your question on our website, bytes.com/spacenuts. We'd love to hear your voices. That's it, Fred, for another week. Thank you so much, sir.
It's a great pleasure, Andrew, and it is great to hear our listeners' voices. I'm just thrilled with that. So thank you to everybody who's sending in questions in their real voices, and thanks to you, Andrew, too, for using your real voice too.
Yes, it's certainly not an unreal voice, but it is one that I'm stuck with, so I use it to the best of my ability. I should also point out we're going to upload some bonus material to our supercasters and patrons, so stand by for that. But Fred, thanks again. We'll talk to you again next week.
Sounds great. Look forward to it, Andrew. Take care.
That's Fred Watson, Astronomer-at-Large, here on the Space Nuts podcast. And thank you, too, for your company. We look forward to joining you again next week on another edition of Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.